Right. This talk is, I think it was titled something like a selection of recent results in VASS. I'm just going to talk about some of the most interesting parts from papers that I've been a part of between the last time I was here, almost exactly 1 year ago, and today. And there's, I think, kind of two halves. I want to emphasize a really interesting idea that I think first appeared in a paper by Rackoff and then reoccurred in a paper by Anthony Lin in 2008. I think he independently found the result and didn't realize it was in the details of Rackoff's paper. And it's a really useful technique for showing upper bounds for certain VASS problems. And I'm going to show two very different problems whose proofs have a surprising amount in common. And I just kind of want to highlight this. One, VASS extended with integer, well, additional, right? It's hard to name this model. Integer counters. I won't say so much, but on transitions, the vectors are all in z to the d plus k. D will be the number of n counters, the normal VASS counters that must remain non-negative, and k will refer to the number of z counters. These can go arbitrary, below 0 or not. The VASS can't tell. But the vector updates are all in z. It's just that the configurations, so if this is p, this is q, the configuration p x has x in n to the d times z to the k, right? This is the extended with integer counters part. And in this paper, we looked at kind of four major cases. When d is 1, when d is 2, when d is 3, and then when d is variable, i.e. any fixed number. And we also compare VASS reachability with a fixed number of n counters and no integer counters to this model. The high level, let's call it sort of philosophical top motivation was VASS is hard. We don't know much about 4-VASS or really anything about 4-VASS. We certainly don't know much about 5-VASS, and certainly 6 and 7-VASS are kind of alien. Maybe there are some ways of shoving integer counters into natural counters, and so maybe studying this model as an entry to attacking the bigger problems is a good idea. Another is that this kind of machine pops up a lot in VASS research. Imagine you're doing unboundedness, and if you read Rackoff's paper, there are certain moments where he'll consider a prefix, and then he wants to find a suffix that's non-negative on the first, x counters, and on the d minus x counters it's integer. Ultimately, he's considering this model. Sure, it's just recoverability, but he's doing something on a mix of these models. Similar with KLM. At some point, if you pump, right, in one of your SCCs, you pump a counter, it becomes arbitrarily large. You can see this as a Z counter, and you really do treat it like a Z counter in KLM. And so maybe it makes sense to study this by itself. So, theorem 1, which is reachability, is the bit I'll talk about now. And then it doesn't matter what the encoding is, unary or binary. I'll touch on this in a moment. In unary/binary, and then the notation we use is this. So this is the number of n counters. If you wanted a fixed number of z counters, we would stick a k there and say 1 VASS plus kz. But if you don't put a k here, this is a non-fixed number. Of z counters. So reachability in this system is in NP, and this is more of a side statement, NP hard. So it's NP complete regardless of the encoding. This is why I'll touch on this. Our main result is the upper bound when this system is encoded in binary is in NP. That's the highest upper bound you could hope for. And the lower bound, NP hardness holds for unary. which is why I've written that in some sense the encoding doesn't matter. There are two ways of getting the lower bound. So you can either have a binary one VASS, right? And you've probably all seen the proof that you can shove subsets out into this, probably more than one time. So that's one option. Or unary integer VASS is NP hard. You can directly do SAT. You could also do subset sum if you wanted. You can take the binary encoding of numbers and put them on different counters. So you can get reachability for the system where you just have a binary VASS counter, or you have as many integer counters as you like. That's for hardness. But the NP upper bound is interesting. And I think it makes sense to give you the scheme. I'll highlight the most important part of the proof, in my opinion, and then I'll talk about it in a bit of detail because I'm sure you've read it. I don't want to bore you too much. Unfortunately, the proof was a little bit awkward. You first have to get an exponential path before you can start massaging it to a nice form. So I'll tell you the goal. Identify a nice form. In fact, what we'll show is that this nice form is linear path schemes for reachability. So to be precise, we'll get something like E, let's say 0 goes to Q0 if and only if P0 goes via, let's say, a path pi to Q0. And to be clear, this is via valid configurations where only the first counter has to remain non-negative, where pi equals, and it's going to be a linear path scheme, right? So segments like tau naught, gamma 1 to the E1, tau 1, tau k minus 1, where the length, so length of all the taus together is its most polynomial we'll get there. And each of the gamma i's are small. Is that still visible? Yeah, it's still visible. Cool. Of gamma I is, well, in this case, it'd be really small. It'd be the number of states. So if this is in the this would be less than the number of states. EI is going to be poly something. I believe we have poly Q and log of norm of T, roughly. I think that's it. Length is good. Length is good. They're small. If you get all of these, you can guess them in NP, right? You can just write down the path that's underlying. You can write down the cycles, and you can write down EI in. Oh, sorry, no. It's poly Q and norm of T. But once you write them down, you get something like log of norm of T. So only polynomially many bits when you encode the system in binary. So that's the goal. But first, so we're going to use a technique from Rackoff, which is what I wanted to, like, the main idea. I think there's two main ideas, but the one I want to advertise, I think that this technique can solve more problems than we realize, is rearranging and replacing cycles. So the final part of the proof will be to take a run and hit it with a load of hammers, remove some cycles, rearrange them, replace them, and replace them into the run to get the form that we want. Before this, there's a preliminary step. Which is if P0 goes to Q0, then there exists, let's say, rho, to be clear, such that P0 goes via rho to Q0 and length of rho is less than poly Q. I believe, I'll just check exactly. I think that's the bit we want most. Okay, so the exact statement is that this is N. Okay, so these are the number of integer counters, and N we define to be the one more of the VASS. So it's an exponential length. But I won't prove this in detail, but the proof idea. Simulate a one VASS Z with a one counter automata. Yeah, we don't use the zero tests, but doesn't matter. Whose alphabet is sigma equals A1 B1 to AK BK. The point is that the alphabet size is twice the number of integer counters you had. Very roughly, the one counter, the OCA, right? That's the one counter. Tracks the N counter. Let's give this guy a name. Like one Z of. And the second is that AI, the letters, and BI track, and put track in quotes, so I'll explain what I mean in a moment, the ith Z counter. Here, if you see something like Zi plus equals 1, that's saying that you increment the ith integer counter, then you want to read AI. And if you see Zi minus equals 1, then you want to read BI. So you track the number of times you increment and decrement. So at the end of a run, in the word accepted by or recognized by the one counter automaton, the number of A's will be equal to the total positive increments to the Z counter, the ith Z counter, and the BI's will respect the negative. So if you want to do reachability, right? So if you want to say that you reach, say P, reach Zi 0 is pretty useful for saying this, then the number of AIs read equals number of BIs read. So we use a paper. I'll tell you which one now. I want to be careful with the citation. So it's a really long paper. She's the cook. Good. It's a lot of authors. I need this half me. think that's the correct one. And Z. This is, to be precise, Lix 2016. And you're looking for the phrase regular extractions. Of one counter automata. They show that you can take one counter automaton, take its language, so let's say L of A, and you can describe its Parikh image very easily. So you can take the Parikh image and describe it as a union of, I think, very small, these are all small linear sets. I won't go any further into the details. And I think the number of elements in the union is also relatively small. It's based on the size of the machine you get. But the point is that it's semi-linear, and we only care about the counts of the A's and B's at the end. So this kind of has a good feeling for us. So what we do is we generate this one counter automaton that in some way respects the behavior of the one VASS plus Z. And then at the end, we want this kind of condition, right? We want, for every I, AI equals BI, and we just write this down as a semi-linear set, right? So if you want a vector, because the Parikh image of a word here, right? So if you have a word in sigma star, right? You can view this as W belongs to N, or to the Parikh image of W belongs to N to the sigma, right? This is a 2K dimensional vector telling you how many times you took each letter. And we want the condition that W satisfies, so we would like sets of vectors, let's say V in N to the sigma, such that for every I, V AI equals V VI. Yeah? I mean, this set's really simple. It's, it's ridiculously simple. So this is semi-linear. You can, if you want to see how this is semi-linear, you can describe it as a single linear set with the generators that consist of basically identity vectors, but they have two one components. So this is the linear set of the zero vector and the set of periods where you have 1, 1, 0, 0, and the next one is 0, 0, 1, 1, 0, 0, etc. Right? So you get k many of these generators in your done. So now, let's give this linear set a name. Let's call it, I don't know, E for equal. Then we care at the very end to look at the Parikh image of the language of the one counter automaton that came from V and intersect it with E. And if this is not empty, then we know there is a word whose Parikh image satisfies the condition that the number of AIs equals the number of BIs, right? Which is saying that you get to a final state, step one, right? You get to Q, basically. We'll just mark this as the final state in A. And then you have the condition that all the A's equal the BIs, that's you reach 0 on all of the K integer counters. And this condition tells you that the run in question was actually a real run, right? Like the n counter never went below 0. And if you really want, you can ask for, you can just stick an equality test at the end, right? If you want, you can have this. If you want to make sure you hit exactly 0. So yeah, we do use an equality test. But I think they talk, when they're talking about the language, I think they talk about the reachability language anyway. So, but if you only have coverability languages, one counter automata who only accept by final state, then you can just add this 1, 0 test. So that's the whole, I went into more detail than I thought I would. This is really nice. I've used this result a couple of times here and there. There was a paper, it was on our Fox paper, we used this idea once, where there was a moment in which we had a 2 VASS and one of the counters became integers. So we had 1 integer counter and 1 natural counter. And we cared to do some sort of reachability. And it was convenient for us to represent as a 1 counter automaton whose letters were capturing the behavior of the Z counter. This is all to say, right, this is really where the science is. The exact size of this set is important. This linear set E is very small, and we use another paper to say that the intersection of 2 semi-linear sets itself is also relatively small. All of this pushes through, and we're able to get this bound. Questions so far? I'm getting the impression everything's okay. You have until I finish rubbing out this board to think of a question. I know I went very quickly, so seriously, just tell me if something didn't make sense. I'll go into more detail or re-explain. Okay, well, you run out of time. Now we've got exponential length parts, we're going to massage them down. This is really where the juice is. We're going to massage these runs down into runs that are of the linear form, the form I just rubbed out. So, given let's say just an exponential length run, let's say from P0 to Q0. To just add a note, the 0 to 0 is not very important. You can add a vector to initialize your system and another vector to finalize your system. They do technically change this definition of n slightly, because if you were to modify the system to be 0 to 0, you would need transitions at the beginning and the end that add the initial and the target and subtract the target vectors, which means that they can dominate this term. So you can either include them in the system, but remembering that the source and target are included in the 1 norms, or you can not include them in the system and just add the norms of S and the norms of T here if you want to. Like it's not critical. But for the sake of the presentation, it's just nice to have 0 to 0. Okay, so imagine this run and just imagine the sequence of configurations, right? So it's going to be something like P0 equals Q0 X0, then Q1 X1 Q2 X2, all the way up to Q, let's say L, right? Whatever this L is, XL. And this is the final configuration. Yeah. So the first thing we're going to do, it's going to be hard to see in advance why, is mark the first and last observations of each state Q and Q. If a state does not occur, doesn't matter. If a state only occurs once, you just put the 2 markers on top of each other, also doesn't matter. So there'll be a marker here to say this is the first time you saw Q, and maybe it has a map. Let's say this is the marker for Q, and maybe you see it later. So it's the end marker. Then maybe here, this is the first time you see P, and then later you see P. And you get the idea. You put these first and last markers down. They're going to occur in kind of, obviously the first occurs before the last, but for different states, the orders are not clear, right? It could be that you go like, you see Q, then you see P, and then later you stop seeing P, and then you stop seeing Q. Or you could see P for a while, and then stop seeing P, and then see Q, and then stop seeing Q. So the order is not clear, but it doesn't really matter so much for us. The rough idea is sort of general idea. Move cycles with positive n effect early in the run, and move cycles with negative n effect late in the run. To be really clear, if we see a cycle that's a Q cycle, so that starts and ends in Q, and it's positive, we'd like to somehow pick it up, drag it, and plop it down at the first occurrence of Q. And if we see a cycle that's negative, we're going to pick it up, we'll keep the negative Q cycle, and we're going to drop it down at the last occurrence of Q. The reason that this is on the surface okay is the n counter, when you do these kind of shifts, will only increase during the infix over the move. So if you pick a cycle from the middle and it's positive and you move it earlier, then the effect of the infix between the shift point and the placement point is going to just go up. And the Z counters don't care, right? They're silent and they don't care where they're taken.
So what if your cycle contains a mark?
Yeah, so this is an important point. This is why the marks exist, is that we're going to treat the marks very carefully. So if you pick up a cycle, let's say there's a Q cycle, right? I don't know, it's like here. And it contains a mark for P, you're not allowed to touch it. In some sense, this is forbidden. So now I'll give you the procedure for picking cycles. We're not going to move them immediately. We're going to pick them, put them in a bucket, and then later we're going to inspect the bucket. So to identify, let's call them movable cycles, or rather it should be replaceable actually, that's much better. So a cycle is replaceable if it is simple and contains no marks. Doesn't matter what kind. And there's a claim. If L is greater than, and I need to get the exact polynomial, I think it's 2q squared plus q, bear with me. Two q squared plus q, yeah. I think maybe greater than or equal to. This is a number that comes out of pigeonhole principal argument. You should just think about this as relatively long, but still polynomial is important. Then there exists a replaceable cycle in, well, I can give this guy a name, let's say pi. The idea being, if you have a section that's length q plus 1 without any marks, then it must contain a simple cycle. Which means that, let's play a game. How long until you run out? So let's put a mark somewhere here, and then you have another block, and you have to put a mark in here. And how many marks are there in total? Well, there's at most 2 for every state. So you can play this game for 2 times q many blocks. And as soon as you run out, you have a final block, you've got your final mark. As soon as you have one more block, there must be inside of this simple cycle without any marks. This is where this number roughly comes from. It's something like 2q plus 1 many blocks times q for, there's some small arguments for shaving it slightly down, but this would give you 2q squared plus 1 times q plus 1. But anyway, the point is if you have polynomial length, then you have a replaceable cycle. Make sense? Any questions? Super. So now, when you find this cycle, so find such a cycle. Oh, I should say, if you start with a run that's short, then the problem's really easy. In NP, you can guess a run that's polynomial length. So for sake of assumption, we're imagining L is big. Like actually exponential makes this interesting, yeah? So if you find such a cycle, and then you've got to identify its type. So there are 2 things that contribute to its type. The starting state of the cycle. That's Q in Q. And is the N effect positive or negative? If it's negative, we're going to try and move it later. If it's positive, we're going to try and move it earlier. But for now, we're just going to put it in the bucket of cycles that are at Q and that are positive, or the cycles that are at Q and negative. So you should think of these buckets as just arbitrary multi-sets of cycles, where you might occasionally pick out the same cycle multiple times. So this is a multi-set of cycles. I'll now pause and give you just a tiny bit of intuition. We can now write down the run. So you repeat this. You can repeat this over and over again until you get L small. So you should imagine the cycle being removed, put in the bucket. You forget about its length. You get a shorter pi, a shorter pi, and a shorter pi, and a shorter pi. Eventually, you'll get to a small enough pi like this, where you should think of it as like a small skeleton. Right? This is L less than 2 or less than or equal to 2q squared plus q. And fairly frequently, there are these marks. Yeah. And now they're marked, right? This is like P, this is Q, this is, you maybe stop seeing P, and then you start seeing R, you stop seeing Q, and you stop seeing R. I don't know. And then you'll place here C plus P. Here you'll place C Q plus. Here you'll place C minus P, etc. Yeah? So we're going to put the positive P cycles at the first occurrence of P that was marked, and the negative cycles at the last occurrence of P that was marked. And note that this would make, if you take any order on these cycles, this makes a valid run. So the Z counters don't care. Nothing changed the effect, right? You've only just moved cycles around, so the overall effect is the same. And the only thing that really changed was when N received its positive and negative updates. And this has the variant that you only move positive things early and negative things late. So this is a valid run. The problem is that this run is not easy to describe. Right, I could put exponentially many different simple cycles in this bucket. And so I haven't really made the problem any better so far. And so now, and I wanted to say, well, pause now, this idea of cycle replacement, right, moving cycles, I think is really important. Like, I really want to stress this. And then in the next part of the talk, wow, okay, I might talk for more than an hour. Is that a problem? No? Okay. If you get bored, you can go to sleep. Yeah, this idea will occur again in a very different problem. Or not very different, but in a noticeably different problem. And so we'll come back to this. But it only really makes sense to do this if you can then improve the representation, right? You can ideally minimize the number of cycles. And so that's what this part is about. So now you have time to ask questions whilst I rub off this part of the board.
I remember that when we put cycles, we must put cycle on the state where the cycle which is the lowest effect.
Yes, you should be giving
with
the
the
talk.
biggest draw. I think we've done proof in that board when reading this paper.
You see, say again, sorry, you.
I think we've done the proof in that whiteboard when we read this paper.
Oh, right. So it's, some generations ago, the proof was right here. Yeah, you're right. So.
And I remember we should put cycles on the most negative position.
Yeah, that's a very good point. So when you pull out a cycle, we're going to change the starting state to nadir. Nadir is this lovely word in, I think it's in Hebrew, that means the lowest point. It's the opposite of zenith, which is the highest point. And it specifies like moment in time, say the lowest moment in time. You could say like the nadir of your life, you know, if something was really miserable. Zenith, it's the highest. As a bonus note, there's a watch brand called Zenith, which I think is a really nice name for a watch brand. Anyway, you don't want a watch brand called nadir. Yeah, so instead of taking the cycle at Q, there is this tiny weeny issue, right? Like if you have a Q cycle that does this, so this is on the N counter, right? And this is like time in quotes, really state by state. Yeah. This moment, if you shift the run early, it could be that this cycle, let's say gamma, you originally take it from a configuration like Q100, and this drop, I don't know, let's say it's -50, is survivable, right? And then you come up to Q, I don't know, this is the overall effect is +60. So you get to 160. And if you shift it earlier, you might be taking it from Q40, right? Which is terrible. So instead, you rotate this cycle. So if this state is, let's say N for nadir, that's a terrible choice. Let's say R. Then you rotate it by this, but this prefix must be taken over here. So this is now an R to R cycle that is monotone with respect to the starting point. So instead of this, we'll consider the R to R cycle that occurs just around it, and then we're free to shift it. Thank you. Okay. Any more questions, or should I say any more corrections? So I'll skip over the last bit quickly because you get the impression you guys will really know this about before. We're going to use Carathodori. Argument on, like, let's just say CQ plus. It's going to be the same for any C set. This is number 3. There's this beautiful result that I'm sure you're familiar with. It's the Carathodori argument of integer cones. It states that if inside of a cone, the integer cone, you have a point, then there exists a small support set of vectors for that point to reach it. There is logarithmically many vectors in the cone that you need to use in order to reach V. That's exactly what we do here. So we take the sum of all the cycles in the multi-step of the effect of the cycle. We'll call this overall E, right, for effect. This guy belongs to Z to the A plus 1. And then we take a small support argument. So there are, to be clear, we need a bound first on this. And we can basically make this bound. Think about what happened during the construction. The worst case is that you always put cycles in Q plus, right? Every single cycle goes in here. And in the worst case, every cycle has length 1. So the length bound from earlier is a bound on the size of this guy. This was exponential, right? This was this, what was it, NKC. Okay. So there exists a sub-collection, let's say C inside of CQ plus, such that there exists let's say N1 to N, so counts for each, such that N1 times the effect of gamma 1, let's say this is gamma 1 to gamma, like that. So now the point is that from Simbrand I think that's the step, although I'm suspicious of this bit, 05. This can be done with C less than or equal to roughly log of the original set, so that is size of CQ. Which gives you something like a constant times K times log of NK, which is polynomial. Roughly, this is less than you can certainly say K k squared times log n. And remember, n had the one norms of all the vectors, right? So, or transition vectors. So this is polynomial, even if they're encoded in binary.
Yeah, so you can also bound the size of CQ plus by something like the size power number of counters,
Size, power, number of counters.
because every cycle is simple. So their length is bounded by Q.
Yeah.
And the norm of the effect is bounded by
That's
size.
probably a better way of arguing it. You're just doing a basic counting argument on the
Yes.
possible vector effects. That's quite nice. It doesn't change the message, but it is an improvement. Yeah, it's nice. So
It still works with this counting.
yeah, gamma belongs to CQ plus implies the effect of gamma belongs to minus Q times like the max norm, yeah. Yeah.
Yeah.
So then the size of this is at most the number of entries of this vector is 2qt plus 1 k plus 1. Yeah, that's better. That's better. It's really nice. But the point is when you log the whole point is when you log this through, this guy gets logged.
Yeah.
That's the critical detail. Yeah, you've improved my C substantially. Very nice. And yeah, this also doesn't depend on S and T.
Yeah.
That's nice. It's really nice. Yeah, and it doesn't matter how you handle S and T. Because in the original system, if you include the initialization and target, like plus S minus T, they're never part of cycles. So they won't ever appear here, which is nice. Okay. But yeah, now we can replace CQ with this count. You then need to bound these values, but you can do this again. If you want, you could write an ILP for this thing and then use ILP bounds. You could probably just derive it directly from this. Yeah, I think ILP is the right way of doing it. So I then write this equation as an ILP, bound n1 through n size of C, and then your description of C plus Q is you replace it with this thing, gamma 1 n1, gamma 2 n2, etc., gamma c nc. So now if I come back to this, instead of placing in C plus P, whatever, you replace this tiny chunk of linear forms. So here you get, I don't know, gamma 1 and gamma size of C, n size of C. And this thing is polynomial. So if you remember back to the linear form structure, right, it's path cycle, path cycle, path cycle. Here there are something like q squared, like 2q squared many of these segments. And in between, there are these empty segments, right? Like no path between these cycles. So there are 2q squared many of these blocks, and inside of each of these blocks, there are size of C many points. So you can add all this up. This is still polynomial. So you get polynomially many path segments and polynomially many cycles. Every cycle is simple because they were real cycles that came from the real system. And you use ILP to bound these guys, which was the bounds that we wanted for the exponents. Everything's polynomial. Yay. Any questions? We resume.
Yeah.
Excellent. So now we're talking about unary weighted finite automata. Do you guys work on weighted automata at all? No. Excellent. Now to refresh. Chrobak. He's a Slavic guy. Chrobak. Have you seen this normal form for unary NFAs? No. Oh, okay, you're in for a treat. Okay, preliminary talk. Rackoff normal form. I learned this early in my PhD, Rackoff normal form, and I didn't use it, unfortunately, and I think it's really beautiful stuff. We have a really good understanding, or rather Chrobak had a really good understanding of unary NFAs. So first, a unary NFA is literally just a directed graph where you can write down on an edge either the single letter, let's say A, or it's an epsilon edge. And the languages of unary NFAs are very simple as a result. Let's first think about what a unary DFA is. A unary DFA is literally just some path, right? It states along, and then a cycle. And everything's labeled by A. The only freedom you have is where you put your accept states. Right, it's a pretty boring model. You can't branch because that would be not deterministic. And so this is all you have. And so the languages here are arbitrary prefixes. So you can have arbitrary steps in your prefix. And then you have periodic behavior in the cycles. So you can say something like arbitrary step here. Then you get this length value, let's say L. And then you have L plus R mod, I don't know, C for the cycle length, right? This is length C. Because, and that's it. These guys are super simple. And what Chrobak proved was that unary NFAs can do more, but not much more. So he has this lovely Q squared time construction. Takes a unary NFA, let's say n, and converts it to one of this form. So they're the prefix of length q squared to a particular control state, which has a single epsilon, oh, and everything here is an n. So it's a quadratic length path. Then a branch with epsilons. So there's the one non-deterministic split. And then here you have cycles that are deterministic. That's it. And they all have A around them. That's it. That's gamma 2. This is gamma K. K is less than the number of states, and length of gamma I is less than the number of states. Less than 2. So you can view this language as some strange quadratic prefix followed by one split into one of linearly many short cycles. So these are all very basic linear sets. So you get different congruences, right? You can have even lengths and odd lengths and lengths that are multiples of 5 or whatever. So you can get some interesting behavior, but not much. And this happens in Q-squared time. There are fine-grained complexity conjectures that people have used to prove this is basically optimum. It's a really nice result. But I will say something really interesting. I can't remember the year of this paper. It's old. It's a pretty good read, but it's wrong. There's a critical error in the paper that's really hard to spot. I know you guys will find it if you try. It's actually a fun challenge, right? Next time you have a master's student, tell them there's a bug in this paper, find it. I think it's 78, but I want to find that now. 86, I was off. This is 1986. And the rough proof, which we'll see for weighted automata soon, it's going to be similar, is very much like Rackoff's. So what he does is he creates a structural lemma. He says if a word is accepted by the unary NFA, then there is one with a linear form that has a small prefix, a single cycle, not multiple cycles, but a single cycle, and then a short suffix. So he gets a lemma like this. And this guy can be taken potentially many, many, many times. And then the idea is from this, because you're only reading the letter A and there's no counters involved, you can just move this to the end. And it's then possible to say that, well, there are runs of type gamma 1, runs of type gamma 2, runs of type gamma k. Here you will see that there are not many k. And so you can have runs of the format, say this is gamma I, like this, where the gamma I comes at the end. So it looks like that section. And then what he does is he takes these runs of this form, and you can say that the union of this thing, right, the union of this piece, comma, this piece, comma, this piece, captures the language, as long as you show that for every word, there is an I such that the run looks like this. And then once you move the cycles to the end, you can then kind of collapse the prefixes. So imagine, we'll look at this one example. You have a run like this is gamma 1. Let's say this is length 10, just for argument's sake. And it has some accepting states, some non-accepting states. Yeah. Then you have one of length, I don't know, 20, with some accepting states and some rejecting states. Step 1, use this cycle and unroll it to expand it to length 20. So you'll have like a copy of gamma 1. Let's say gamma 1 was length 5, right? You have gamma 1, gamma 1, and at the end you have gamma 1 again. And you mark the accepting states that gamma 1 gave you, yeah? So now this prefix, let's draw it to scale. This is gamma 2. This is now two very similar shapes, right? They've both got prefixes of length 20 and cycles. You can now union these together by looking at these control states. And if either is accepting, we're going to put this as accepting here. So let's say this is Q1, this is P1. If PI, right, or QI accepting implies RI accepting, where RI is this guy. So you kind of union them down. So some of them will remain non-accepting. Here, that's accepting, that's accepting. So we have loads of accepting. Okay, I've not done a very good job, but there might be a non-accepting state here. I don't know. And then notice that we can't, in this machine, you basically have this behavior. You either choose the top branch or you choose the bottom branch. You can merge the branches, but you can't mix gamma 1 and gamma 2. You can't take gamma 1 and gamma 2, then gamma 1 and gamma 2. So we need this branch to say, well, you then have to go to either gamma 1 or to gamma 2. And that's very roughly some of the ideas in Chrobak. But the critical bit happened earlier. It was here. It was this form. And the way he gets this form is the same as how we do it, and Rackoff does it in our paper. You take a run for a word, you mark, instead of marking the first and last occurrence of a state, you just mark the occurrence, like let's say the first occurrence of a state. We'll come to this. So it's not about weighted response, it's still about unary NFAs. So let's say you first see P here and you first see Q here, you first see R here, you mark the first occurrences. It doesn't really matter, you just need to mark one observation of each Q. First is nice to think about. And then you do the same thing, you do cycle removal. Remove cycles. So you get the same idea. Once you've maximally removed cycles, the skeleton you're left with is short. This time, instead of being 2q squared, it would be q squared, because there are q many markers, right? Not 2q many markers, but ultimately the same argument. And then you do there's a different step now. So in our paper, we then use Carathodori on these big k+1 dimensional vectors to do replacement. Now, once you've removed cycles, let's say you've got your cycle multiset. Inside of here, we're gonna, to be really clear, because there's no like counters, no push down stacks, no nothing. If you have a state R and a cycle, you can move it anywhere. It does not matter. It's just reading 8. So that's why we only do one mark. Sorry, I should have made that clear. So now from this multi-set, you have like just loads of cycles, gamma 1, gamma 2, gamma 3, gamma k. And they're at various states, right? I didn't say which states they're at. I just put them all in the same bin. But the state doesn't matter at all. There's no nadir. And so what we'll try to do is maximally replace all of these with some cycle, let's say gamma I, and try to do it as many times as possible. This will then give us a nice description. But it might not be very easy to do this, right? It could be that you can't swap all of these random cycles for many copies of one cycle. But the following is true. If the size of C is greater than Q, then there exists a subcollection such that the sum of like lengths of gamma equals, well then, yeah, for any L, L, yeah, belonging to 1 to the size of Q. So this quantifier comes first. There exists C prime in C such that the collection of cycles that you chose is some multiple of L. What does this say in more detail? So this says that if you have a large enough collection of cycles, but like that large, you can pick some subset of them to be a multiple of any number you like. Obviously, if you choose L as 1, this is trivial, just take one cycle. But if you take L as Q, not obvious, because I could have inside of C, right? C could be cycles with lengths, I don't know, like 2, 7, 9. And if you have L as 10, it's kind of what? You need more, right? You need at least 10 many items, right? It's kind of not clear how you collect them so you get a multiple of 10. Like, that's not an obvious statement in my opinion. This requires like some thought. But the point is that now you can choose any cycle you like. Its length is between 1 and Q. And I promise you, if my set of cycles is sufficiently large, then I can take some subset of them and replace them with copies of gamma I. So the choice of gamma I is arbitrary. You may as well choose the first cycle. Literally the first cycle you see is going to be the special cycle. And what you're left with, so you can keep repeating this until you're left with C as size of Q. Right, because if C is bigger than the size of Q, then I can take some and replace it with gamma I. Take some and replace it with gamma I, and keep doing this. And you terminate when this is true. And then you give up. You say like, oh, I tried my hardest. And then you take the cycles that are left, let's call them like the, I don't know, the waste cycles, the scraps, and you reinsert them back into the run where you marked states. And then you expand the underlying set. What's this? Well, every cycle in here is simple, and there are not many of them. So the waste cycles that you end up with, there's only, the length contribution is Q squared. So you're only reinserting Q squared amount of cycle length back. And you have this huge guy here. So there is some special gamma I. You're going to take loads of types. And now this is of the form you wanted, right? You have, okay, technically it's 2Q squared because there's the skeleton and the waste. That would be 2Q squared. And there's one cycle you take. That's it. That makes sense. This is the alternative. This lemon here is the alternative of Carathodori for this system. Did that make sense? Are there questions? Great. Thank you. You're the most junior, right?
No.
No. Wait, who's the most junior? You're the most junior.
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 You
We're the same.
Oh, you're the same. Okay, okay. If the most junior guy understands, then everyone understands, right? So that was a rough idea for Chrobak normal form, and we're going to use the same idea for unary weighted finite automata. So the nice bit is if you want to, let me motivate a little bit, Rackoff normal form, I forgot to do this. Rackoff normal form is so simple. If you want to decide properties like, is the word, if I give you a word length, is it accepted by a unary weighted finite automata, then you can compute the Rackoff normal form efficiently, given the NFA, and then it's really easy to check word lengths, because you're just asking, well, is it short? If yes, you just check the prefix, and if it's longer, then you just look, is it like a multiple of X mod Y? That's also very easy last time I checked. And so checking membership for these systems is simple, and checking universality is simple. You're just asking, is relatively simple. You're just asking, does this linear set cover the natural numbers? Which is, okay, it's not as easy, but still, I think it's code if you complete. But yeah, it's not difficult. Okay. So unary weighted finite automata, I'll describe it in words, and then if we need, I'll put symbols on the board. It's a unary NFA. Wow, that's one I showed to you. But you also write down numbers. So you write down a number in Z on every transition. And unary weighted finite automata don't accept words in the same way. They kind of do. So there are accepting states, and there are non-accepting states. You can say a word is accepted if it reaches an accepting state, but what we really care about is a function. So the unary weighted finite automata, if I call it A, defines a function, like its own function, from n to z or minus infinity. So there are accepting states, and if you take a word, a to the n, and there is no path from an initial state to any accepting state, then its weight is minus infinity, rejected. If not, look at all paths, pi, and in pi, you add transition weights. So you can think of this as an integer one VASS. Right, you're adding the weights, and then you take min over pi, and that will be the weight. So the weight of A of n is the minimum of the sum of pi, if I use this sort of illegal notation, such that from the initial state, let's say qi, 0, you get to some final state with some value, right? This is actually sum of pi. And QF must belong to a final state. So if there is no such run, the minimum of the empty state is minus infinity. So that's why this comes out. Does that make sense? It's a pretty simple model. In some sense, it's kind of like coverability and all that. So it's kind of got that feeling, sort of. If this doesn't make sense, you've got to tell me. Otherwise, the remainder of this talk is going to be awful. All good? Okay. I'll just give an example, because I think it's nice to see an example to get a feeling for what's going on. They behave differently to VASS. I think that's important to observe. The language is anything of length at least 2, but the weight function is a bit awkward, right? Basically, what this machine allows you is for relatively short words, so words of length up to something like 50 or 60, you come down here, because this weight is much smaller than this weight. So you're down here, your length, so A of n is n plus n minus 2 times 2. And up here, your length is A of n is, or your weight, sorry, is 100. Also, this should be 0. Plus n minus 2, right, times 1. So at some point, these overlap, right, because reading A's here is more expensive than reading A's up here. And so it's kind of not clear, like, what you would do for a weighted automata. Like, how do you come up with small versions of weighted automata? Because this behavior looks kind of nasty. It's like you can have big binary encoded weights that can offset when you use one cycle versus when you use another. Like, this is such a simple machine, but it already has slightly interesting behavior. Something that you definitely don't see in unary NFA. And to be clear that, like, the overlap, right? So the actual function is therefore min of these things. Yeah. For like n at least 2. Otherwise it's massive. We have a theorem. So now that you've got a feeling for these guys, I can go further. I want to make sure I get everything. So there are 2 theorems. I'll start with the basic version, then I'll show you how to, like, turn it into a Rackoff form. So there exists deterministic unary weighted finite automata B1 to BK such that 1. Oh, I should say, given a unary weighted finite automata A, right? So you start with, you're given a non-deterministic one, and then you're going to find these deterministic guys, such that, well, for every n, like the obvious property, it has equivalent weight. It's the same thing, it has the same language, right? But for weighted automata. For every n, A of n equals min of B1 to B, or B1n to BA of n. Right, so the union of the deterministic machines is equivalent to the original. 2. There are not many of them. That's the states of the original machine. And this is all about size now. For every, because we want, I could give you massive machines if I, gave you a terrible theorem. It's not very useful. For every k, b I, well, sorry, for every I, bi has at most 2q squared plus q states of transitions. To the greatest transition effect that you see in these deterministic machines is small. So it's relative, polynomial relative to the maximum update you see in the first machine. And it can be computed polytime from A. So it's not just guess. You really have to, you can really just compute these things and massage them. Does the statement make sense? To be clear with the shape of this, when I say non-deterministic and deterministic, I'm talking about the underlying machine. So deterministic unary weighted finite automata has the same shape. It's just this like lasso, right? Spoiler. It's the same proof. There's a reason I've been showing. Well, it's not the same proof as Chrobak because you have to respect the weights, right? Like this machine in some way has to be accounted for. But you can make the same argument. But I won't go into all the details because I've been talking for longer than you probably wanted me to talk to. But I will highlight some critical differences. So at first, if I make the following claim, any word a to the n has a run right that you might take many times, where this is relatively small. You kind of should be a little bit alarmed, right? So anywhere, let's call this guy pi, where a of n equals weight, or if I use this notation, some. So this is saying the minimal weight is achieved by a run of this small linear form. This makes sense for unary NFAs because when you find a cycle, you don't care about anything other than its length, and so you can trade them off, right? Remember this counting argument that I was talking about. But here it's a bit trickier, right? I need to maintain the weight. It could be that I have many cycles and each of them have different weight. So it's kind of unclear. I can't just replace one for another because it might change the weight. Well, at any given moment, we're going to minimize the weight. That's the nice. So the argument is the same. But inside, but there's like a pre-processing step. Let's say rho be a minimal weight run for AN. Inside of this guy, identify the minimal average weight cycle. What is that? So to be clear, imagine this cycle, I don't know, A10, A10, versus this cycle, A5, 5 is terrible, let's say, A20, A0, A0. Then this guy is more efficient. For every A, you're reading 6 and a bit to your width. For every A here, you're reading 10. And so in a really long run, if you take this cycle, imagine you take this cycle, let's call this gamma 1, let's call this gamma 2. And let's say there's a run where you take gamma 1 3 times, and let's say gamma 2 occurs once for some reason. Then you can replace all of these with 2 copies of gamma 2. By taking this 3 times, you read a to the 6 at cost plus 60. And 2 copies of this is reading a to the 6 at cost plus 40. So you can minimize the weight by trading multiple copies of this cycle from multiple copies of that cycle. Makes sense? So this is maybe giving a hint. So when I say average minimal weight cycle, I mean look inside the run. Actually, it's not even average minimal weight cycle you take. It's average minimal weight cycle at any state visited by rho. And the idea will be that this will be the cycle. Let's give this a name, gamma. this will be the cycle we take over and over again. Very roughly, if you see copies of, let's say, high weight cycles at other places in the run, then you should be able to remove them, replace them with multiple copies of gamma. Remember that cycle order doesn't matter, it's just the weight that we care about. And if you had enough of these higher weight cycles, eventually you'll find some number of them that you can replace with a lower weight cycle, and this would minimize the weight of the run overall, or rather lower it. But this would be a contradiction, as we started with a minimal weight run. So we'll be able to argue that the minimal weight run has the form of some fairly short path, gets to this special minimal average rate cycle, takes it loads and loads and loads and loads of times, and then a short enough run to the end. So I'll show you the details. It's basically the same as before. So